Today we're going to talk about exponential growth and exponential decay models. And an exponential growth model has a similar formula to an exponential decay model, and it looks like this. F of t is equal to c e to the kt power. And I'll tell you what all these things mean. First of all, f of t is time. And usually we count time in years, not always, but usually. K is got to be greater than 0 if it's exponential growth, because this exponent has to be a positive one for growth. And what it's equal to is the growth rate. F of 0, when time equals 0, we call that the initial value. And f of 0, if you plug in 0 in for t, in this original formula, you get c e to the 0 power. Anything to the 0 is 1, so f of 0 is actually equal to c. And c is called the initial value of the function. If you wanted to take a look at a graph, I think you're familiar with this graph. Exponential growth looks like this. And the y-intercept, if you have a formula like this, the initial value is actually equal to c. So this y-intercept is a c. Exponential, so this is growth. Exponential decay is the same as what I just listed up here, except k is less than 0 and k is equal to the decay rate. But everything else is still the same, the initial value, the y-intercept, but it's coming down like this, exponential decay, but the y-intercept is still equal to c. This formula is the same formula as our compound interest rate, because if you remember that, it's A equals P e to the RT. The amount of money after any particular time is equal to the initial value, which is the principal, times Z to the RT, and R is the interest rate, which in this case it's the rate of growth. So it's the same thing as the interest formula that we've been using for the past day or two. So what we're going to do is do a couple of examples of exponential growth. Exponential growth is very common when you're talking about population. So we'll do a world population problem. In the year 2000, the world population was 6.1 billion people. In 2005, the world population was 6.5 billion. What we're going to do is find the annual growth rate and determine the year when the population will reach 9 billion. So what we do, I hope you can read this. What we do is we start out with our f of t equals ce to the kt. But instead of using the letter f, I think is the name of the function. I think I'm going to use the letter p for population. So instead of f of t, I'm going to use p of t. The population at any time t is equal to ce to the kt. Instead of c, I'm going to use, I think you're familiar with this from science class, p sub 0. That is called the initial population. And initial being the very first population that we have data for. Initial population times e to the kt. And k will be our rate of growth. That's what we're solving for. And from the given information, in 2005, the population was 6.5 billion. So 6.5 is the population at any point in time t. The initial population, we'll use 6.1, we'll call the year 2000 our initial population. So 6.1 times e to the power of k, and what is t? T is 5 years, because between 2000 and 2005 there's 5 years. So it's equal to 6.1 times e to the 5t. So to solve this, you know how to solve it. Divide both sides by 6.1. You're going to take the natural log of both sides to get rid of the e, and then you're going to divide both sides by 5 to get k by itself. So in our calculator we can put the natural log of 6.5 over 6.1 divided by 5. And that's the rate of growth. And if we wanted to write that as a percentage, we'd move the decimal place over 2 places, and this is about 1.3%. So k equals 0.0127, which is approximately equal to 1.3%. So there's our rate of growth. Now we're going to try to figure out when the population will reach 9 billion people. So that'll be our new p of t. So that, I'll call that part A of our problem, and this is part B of our problem. When will it reach 9 billion? So we plug in 9 for P of t, and now we're going to solve for t. So 9 is equal to, our initial population is 6.1 times z times 0.0127 t. We're going to solve for t. When we solve for t, we're going to add that on to 2000 to get the year. So we're going to divide both sides by 6.1. We're going to take the natural log of each side to get rid of the e, and we're going to divide both sides by 0.0127 to solve that for t. Natural log of 9 over 6.1 divided by, actually I could just hit second ANS, that'll give this value without rounding it. And so it looks like t is 30.6 years. And if our initial year was 2000, that means adding 2000 plus 30.6. So in the year 2030, the world population will reach 9 billion. I'm going to stop this video right now, and I'm going to upload it because I'm going to do this in 2 parts today.